When you think of chemistry, you probably imagine a laboratory, glassware, solutions, controlled temperatures, a carefully measured environment where reactions unfold under human supervision. Chemistry, as we experience it, requires conditions: warmth, pressure, stability, the gentle collision of atoms in a hospitable medium. But the universe is not hospitable. Most of space exists at temperatures barely above absolute zero. Pressures so low, they make our best vacuum chambers look crowded. Radiation that would shred molecules apart in an instant. And yet, can chemistry exist where there is no warmth, no shelter, no stability? The answer will take us from the coldest corners of space to the hearts of dying stars. Let's begin with what we mean by extreme. In the space between stars, temperatures hover around 10 degrees above absolute zero, 10 Kelvin. Cold enough that motion itself nearly stops. Cold enough that atoms drift in near-perfect stillness. The density is almost incomprehensible. A cubic meter of interstellar space contains just a handful of atoms. Compare that to Earth's atmosphere, where the same volume holds trillions upon trillions of molecules colliding constantly, exchanging energy, forming bonds. Out there, collisions are rare. Encounters between atoms might happen once every few thousand years. And the radiation, cosmic rays, high-energy photons, electromagnetic waves tearing through the void, capable of ripping electrons from atoms, breaking any fragile structure that dares to form. These are the conditions that dominate most of the observable universe. This is where chemistry should be impossible. But in the 1960s, astronomers began detecting something unexpected. Radio telescopes, scanning the depths of space, picked up specific frequencies. Signatures that could only come from molecules, not just atoms drifting alone, but atoms bonded together. At first, simple molecules, hydrogen molecules, carbon monoxide, cyanide. Then, over the decades, the list grew longer. Water, ammonia, methanol, formaldehyde, and then, stranger still, organic molecules, long carbon chains, ring structures, molecules with 10, 20, even 30 atoms locked together. Hundreds of different molecular species have now been cataloged in interstellar space. In regions where chemistry should not exist, it thrives. This is the paradox. So how does it happen? The key lies in something we barely notice on Earth. Something so small, we can only see it with powerful microscopes. Dust. Cosmic dust grains. Microscopic particles, no larger than smoke, scattered throughout the spaces between stars. They are remnants of ancient stellar explosions, composed of carbon, silicates, frozen ices. And they change everything. On Earth, chemistry happens through collisions. Atoms smash into each other with enough energy to form bonds. Temperature provides that energy. Pressure increases the frequency of encounters. But in space, there is no heat, no pressure. Instead, atoms drift slowly through the void until, eventually, they encounter a dust grain. They stick to its surface. Frozen in place by weak forces, they begin to accumulate. One hydrogen atom, then another, then a carbon atom, an oxygen atom. These atoms do not collide violently. They slide. They creep across the icy surface, molecule by molecule, over timescales that span thousands, even millions of years. And in that glacial slowness, bonds form. Hydrogen atoms meet and become molecular hydrogen. Carbon and oxygen combine into carbon monoxide. Water molecules assemble, one atom at a time, on frozen surfaces colder than anything we can create in a laboratory. The dust grains act as catalysts, meeting places, scaffolds where chemistry can occur without the conditions we thought were necessary. This is surface chemistry. Patient, methodical, unhurried. The universe has time. Not all molecules remain simple. In dense molecular clouds, shielded from the harshest radiation, more complex structures emerge. Glycolaldehyde, a sugar molecule. Amino acids, the building blocks of proteins. Polycyclic aromatic hydrocarbons, intricate carbon rings that glow faintly in infrared light. These molecules form before stars ignite, before planets coalesce, before life has any chance to begin. The chemistry of space does not wait for habitable conditions. It creates the ingredients first. But there are limits. As we move toward greater extremes, chemistry begins to falter. Inside stars, temperatures climb into the millions of degrees. Atoms move so violently that electrons are stripped away entirely. What remains is plasma, a sea of charged nuclei and free electrons, no longer bound into atoms, much less molecules. Chemical bonds cannot survive here. The electromagnetic forces that hold molecules together are overwhelmed by thermal energy. In a supernova, the death throes of a massive star, temperatures spike to billions of degrees. Matter is compressed to unimaginable densities. Elements are forged in nuclear reactions, fusing lighter atoms into heavier ones. But this is not chemistry. This is nuclear physics. Molecules dissolve. Atoms themselves are transformed. And yet, even here, the story does not end. When a supernova's shockwave tears through interstellar space, it leaves behind a shell of expanding gas. Initially, the gas is far too hot for chemistry. But as it cools, as it spreads and thins, something remarkable happens. Atoms begin to recombine. Electrons rejoin their nuclei. The first molecules reform in the cooling remnants of destruction. Chemistry returns. Not immediately. Not in the way we recognize it on Earth. But gradually, patiently, the same processes that occur in cold molecular clouds begin again. The universe does not erase chemistry. It postpones it, transforms it, then allows it to re-emerge. This is the insight of astrochemistry. Chemistry is not a fragile process confined to Earth-like conditions. It is adaptable, resilient. It operates under rules that shift with temperature, density, and energy. But it doesn't disappear. In the coldest regions, it slows to a crawl, unfolding over eons. In the hottest regions, it gives way to plasma and nuclear reactions, but only temporarily. When conditions stabilize, chemistry reasserts itself. Astrochemistry studies this continuum. It maps how atoms interact, not just in laboratories, but across the full range of environments the universe provides. From frigid molecular clouds to the edges of stellar atmospheres. From comet surfaces to the gas surrounding black holes. And what it reveals is this. Chemistry is not an exception. It is fundamental. There is a deeper question hidden in all of this. If complex organic molecules can form in the harshest environments imaginable, in near-perfect vacuums, at temperatures that approach absolute zero, under radiation that would sterilize any living thing, then where did the chemistry of life truly begin? We used to think Earth was special, that our planet's conditions were necessary for the building blocks of life to emerge. But space chemistry suggests otherwise. The amino acids in your body, the sugars that power your cells, the carbon structures that form the backbone of every living organism. All of these molecules exist in space, formed long before Earth existed, delivered to young planets by comets and asteroids, carrying the chemical seeds of complexity. Perhaps life's chemistry did not begin on Earth. Perhaps it began in the frozen darkness between stars. So, is chemistry possible in the most extreme environments of the universe? Yes, but not in the way we imagined. Not with beakers and controlled reactions. Not with the warmth and stability we take for granted. Instead, chemistry in space is patient. It is slow. It adapts to conditions that would seem impossibly hostile. It operates on surfaces we cannot see, over timescales we struggle to comprehend, guided by the same fundamental forces that govern reactions on Earth, but expressing them in ways we are only beginning to understand. The universe is not hostile to chemistry. It is simply unfamiliar with our expectations. And perhaps that is the most humbling realization of all. Chemistry does not belong to us. It does not require our presence, our atmosphere, our carefully controlled environments. It is woven into the fabric of the cosmos itself, from the coldest void to the heart of a dying star. From simplicity to complexity. From isolation to connection. Chemistry endures. And in that endurance, there is a quiet, persistent kind of beauty.